This is the chapter 3. The title of chapter 3 is Mathematical Analysis of Material Balance Equations and Process Flowsheets. Actually, you know everything about that because you have learned about that in chapter 2. So let me introduce what is the core content of chapter 3. The first one is more mathematical and rigorous approach for the key ideas in chapter 2. Again, you have learned about the material balance equation and also process flow sheet in chapter 2. However, in this chapter, you are going to the deeper version of material balance equations you will meet in this chapter. The second one is generalized material balance equation from conservation of mass principles. What is the material balance equation? Actually, it is very simple thing. In minus out plus generation and minus consumption is accumulation. That is the most basic concept of material balance equation. Even if you will learn various type of material balance equation in this chapter, but just memorize only this equation. The other various equations would follow this concept. Plus linear algebra to evaluate the flow sheet. Here system and also this system have two streams. Through this stream 1, some materials are introduced into the system, and after some reactions, some materials are going out of the system through the stream 2. This block flow diagram is representing those system and streams. Here, some mass of component A and also component B is introduced into the system. And then something is accumulated inside of a system. Also, some component of A and some component of B are going out of the system. Let me start with the law of conservation of mass. Total mass in the system, I have said, in the system is like that. Total mass of system here is equal to the total mass of component A inside of system plus component B. Of course, there are no generation term and no consumption term inside of the system because we are thinking about the mass instead of moles. There are no increase in mass or no decrease in mass. Let's go to the stream variables. Total mass flow rate of stream 1 and 2 can be described by those two equations. Input is equal to the total mass of stream 1 is equal to component A and component B, of course. You can find the dot over the M. It means mass flow rate. Let me say the unit about that. You know, the M in M system is like a kilogram. However, if you have a dot on the M, it means mass flow rate, kilogram per, for example, hour. How about component 2 or output? Total mass flow rate of stream 2 is equal to, of course, component A and component B. Of course, you should put the dot on the M. That is the typo. So it should be dot and it should have dot like that. Then with those equations, let me think about the change in mass inside the system over the time interval delta t. In that case, something changes inside of the system. So let me say delta m inside of a system is equal to m dot 1, means mass flow rate of input stream, by delta t. The unit of this product is kilogram. Delta m cis in kilogram. This is input minus m dot 2, mass flow rate of component 2 by delta t. That is the amount of output. Then let me move this delta t into the left side of the equation. Then we could obtain this equation. dm cis, it means total mass of the system change dt, is equal to the mass flow rate of input minus mass flow rate of output. This is so-called differential material balance equation of a system. So shortly, this one is going to the title, DMB1. DMB1 means differential material balance equation version 1. 1 stands for mass in my lecture, and 2 stands for mole. So DMB1 means differential mass balance equation. So we have obtained the differential form of material balance equation of a system in terms of mass. Let me think about more specific situation. At the steady state, dm system dt is going to 0, so input is equal to output, like that. Again, the mass flow rate of output is equal to the mass flow rate of input. Of course, 1 kilogram is introduced into the system. If your system is working on the steady state, then the output is 1 kilogram. It should be the same. This equation is about the total mass. And then let me split those total mass version of material balance equation into the component version of mass balance equation. The total mass inside of a system can be split into component A and component B. Also, total mass flow rate of input is going to component A and component B minus output. In the same way, the total output is split into component A and component B. Let me think about a reaction which is A going to B. Then mass reaction rate of component A is equal to minus mass reaction rate of component B. It means 1 kilogram per hour of product is generated. At the same time, 1 kilogram of component B or reactant is consumed. This equation have the meaning like that. Or R dot A plus R dot B should be 0 from this equation. So I can say the total mass is conserved. Let me explain about this notation. The capital R means mass rate. So the unit of this mass rate is gram or kilogram per minute or hour. So let me say gram per minute. So I have borrowed this equation from the previous slide about the component. Again, that is the term for the total mass inside of a system. So the total mass inside of the system is split into component A and component B. It's going to the total mass flow rate of input minus total mass reaction rate of output, component A and component B. It was the original version of the total mass balance equation. There was no generation term and consumption term. Let me write down about input output something. This is what? Accumulation. It's equal to in minus out and plus generation minus consumption. However, for the case of total mass balance equation, you don't need to think about generation minus consumption. Then I have added one more term, actually two more terms. Capital R dot A plus capital R dot B. Even if you don't need to think about generation minus consumption, because in this case R dot A plus R dot B is 0. So you could add this 0 value term into the total mass balance equation. Then I'd like to split those equations into the equation for component A and the equation for the component B. So I'd like to get together the terms about component A. So this one and this one and this one and this one. That is going to this equation. And let's go to component B. This one, this one, this one, this one is going to this equation. So let me think about the component mass balance equation for each component. So the M of component A of the system dt is equal to the mass flow rate of component A in input minus the mass flow rate of component A in output plus generation term. In the same way, you could have obtained this kind of equation about the component B. So something changes. I mean, for the total mass balance equation, you don't need to think about generation and consumption term. However, in the cases of the component version of material balance equation, you should think about generation or consumption term. So actually, the meaning of the reaction rate of component A is about generation minus consumption. Okay, then let me extend this reaction into more generalized version. So here, it is not just A is going to B. This is nu A is going to nu B. Of course, this nu sub A and nu sub B indicate the stoichiometric coefficient of A and B respectively. Also, when you are thinking about the reactions with stoichiometric coefficient, it is better to use molar units rather than mass for reactions. Why? Because the stoichiometric coefficient is a kind of moles. So I'd like to convert the mass flow rate, mass reaction rate into the molar reaction rate. The small r dot means molar reaction rate. Let me think about the unit of molecular weight. What is that? Unit of molecular weight is gram per moles, right? So the unit of the mass reaction rate is gram per, for example, second. And the unit of mole reaction rate is mole per second. So the product of molecular weight and the molar reaction rate is going to, after killing more and going to gram per second. That is the mass reaction rate. Okay, so let me start with R dot A plus R dot B is equal to 0. But MA and MP are not equal to each other. So even if the mass reaction rate, the summation of mass reaction rate is going to 0, but the summation of molar reaction rate is not 0. It's an important thing. Because, sometimes 2A is going to just 1B, where 1A is going to 3B, or something like that. So the summation of the molar reaction rate of each component cannot be going to 0. One more thing, stoichiometric coefficient to relate the reaction rate of component A and reaction rate of component B in terms of moles. For example, 2A is going to 3B. Then the ratio of the molar reaction rate of component A to component B is equal to -2 for A over +3 for B, because A is reactant, and then the stoichiometric coefficient of the reactant should be minus. So -2 over 3. So by using the ratio of stoichiometric coefficient, you could correlate between the reaction rate of each component. So generally I can say like that. R dot A over R dot B is equal to nu A, stoichiometric coefficient of component A per component B. Okay, so for this equation, for this chemical reaction equation, we could define the reaction rate of A and reaction rate of B. Also, the values of reaction rate of A and reaction rate of B are different. However, I'd like to represent this single reaction rate by using a single parameter. So the single parameter to describe the single reaction is extent of reaction, symbolized by xi. This is the Greek letter. So xi, that is the extent of reaction. This is a kind of reaction rate. This Greek letter is pronounced as sometimes xi or sometimes xi. Anything is okay. So let me say xi. And let me define one single extent of reaction for a single chemical reaction equation. Let me start with this equation. So R dot A per nu A is equal to R dot B over nu B here. It means the molar reaction rate of a component normalized by the corresponding stoichiometric coefficient would have always the same value. So extent of reaction of xi is equal to RA nu A equal to RB nu B, or if you have another C component, then you can say R dot C nu C, something like that. So at this point, we have had reaction rate of A and reaction rate of B required to define the reaction rate for the single chemical reaction equation. However, after defining the extent of reaction, you could use only one single reaction rate instead of R dot A and R dot B. That is the xi dot. Some example here. You have a chemical reaction equation like 2A going to 3B. And then let me assume that xi dot, or extent of reaction, is 2 gram mole per second. My question is, what is the value of the molar reaction rate of component B, or R dot B? The answer is 2 by 3 is going to 6 gram mole per second. How about R dot A? 2 by 2 is going to 4 gram mole per second. Let's go to the other chemical reaction equation. Here, A is going to 3 over 2B. Actually, those two chemical reaction equations are the same. And let me assume that this equation have the same extent of xi as the previous example, 2 gram mole per second. And then what is the value of the R dot B? 2 by 3 over 2 is going to 3. Even if I have said those two equations are the same, but the reaction rate of component B are different. It means you should fix the stoichiometric coefficient for defining the extent of reaction. In this slide, you can find a lot of equations. However, you don't need to memorize it. Okay, the first category is DMB1. What is the meaning of DMB1? I have explained about that in previous slides. Differential material balance equation version 1. 1 stands for mass. So this is the differential mass balance equation. Of course, the unit of DMB1 is mass over time, like kilogram per hour. So let's go to the final equation directly. The MACs dt, it means the total, the mass of component A in system is equal to input minus output plus generation minus consumption term, right? This is accumulation term. This is generation term. No. This is the input term. This is output, and this is the generation minus consumption term. Then this is the mass version of material balance equation. So this is the RA, R dot A, mass reaction rate of component A. And this is the small r dot A, molar reaction rate of component A. You should remember the total mass. You should remember the total mass balance equation have no generation minus consumption term. However, the mass balance equation for each component should have the generation minus consumption term. So you should consider the extent of reaction. That is the first category of material balance equation. Let's go to the second. That is the molar version of material balance equation. Differential material balance equation version 2. 2 stands for moles. So the unit of this balance equation is mole per time. And then let's go directly to the final equation. Always you should remember accumulation is equal to in minus out plus generation minus consumption term. So the NA system, moles of component A in system dt is equal to molar flow rate of component A in input minus output plus generation term, generation minus consumption term. So actually this one is molar reaction rate of component A. In the same way, you could build up the mole balance equation about component B. Of course, this one is R B, and the third equation is about total number or total moles of mass balance equations or mole balance equation. So the density system, total moles of system dt is equal to also input minus output plus extent of reaction term with total summation of the stoichiometric coefficient. As you expected, total moles are not conserved. I have said total mass are conserved without generation minus consumption. However, in each molar version of balance equation, you should think about the generation minus consumption term. Let me write down again. Accumulation, input, output, generation minus consumption. Therefore, if the summation of stoichiometric coefficient is 0, then in that case, the total mole balance equation are simplified into dN dt is equal to input minus output. Okay, here is some example. Anyway, you have learned about mass balance equation or mole balance equation, and the number of those equations are about 6, but you don't need to think to memorize all of the equations. Just remember accumulation is equal to in minus out plus generation minus consumption. Okay, let's do with exercise or example 3. N2O4 decomposition. N2O4 is fed to a reactor. Here is the reactor, and N2O4 is introduced. And the known value is the flow rate of the input, 84 gram mole per minute. Where, the reactor, inside of reactor, some of N2O4 decompose to NO2. So here's the balanced chemical reaction equation. N2O4 is split into two molecules of NO2. The reactor operates at steady state and the stream leaving the reactor flows at 1 to 6 gram mole per minute. This value indicates total moles of products and reactants existing in stream 2 or output. So, and that 2 is 1 to 6 gram mole per minute. And in this stream, you can find two different components. One is the reactant N2O4, and the other thing is NO2. The question is, what is the extent of reaction? That is the first job. And what is the molar flow rate of each component in the reactor outlet system? Let me start with the total mole balance equation. So, D and total inside of the system dt is equal to input minus output plus generation. At steady state, the accumulation term is going to 0 and input 84. Total output minus 1 to 6 plus extent of reaction with the summation of all stoichiometric coefficient and minus 1 for reactant N2O4 and plus 2 for the product NO2. So minus 1 plus 2. Then you could calculate the extent of reaction for this reaction. Then it's time to calculate the molar flow rate of each component in the reactor outlet system. So we need to get some values about each component. It is time to use the component version of differential mole balance equation. dNdt accumulation is equal to input minus output plus generation for component A. The steady state, so accumulation is 0 and introduced input is equal to 84 because you would find only N2O4 in the input stream. There are no NO2. So 84 minus the unknown, and that A2 means the mole flow rate of component A, in this case N2O4, minus this one is about the generation minus consumption term. And this value was given to you because you have calculated the extent of reaction from the total mole balance equation. So extent of reaction is 42 and the stoichiometric coefficient of component A is minus 1. Then you could calculate 42 gram mole per minute for the molar flow rate of output for component A. So this is A2. This is 42. And of course you could calculate about the NO2 because the total molar flow rate in stream 2 was 1 to 6. So 1 to 6 minus 42 is going to the value of NO2. Or you could use the mole balance equation about component B or NO2. So accumulation is going to 0 and input is going to 0 because you cannot find any product or NO2 in the input stream. Minus output, this is unknown, plus extent of reaction xi by the stoichiometric coefficient of this product 2. Then you could calculate the molar flow rate of component 2 in the output stream. It is very simple. It's time to generalize the material balance equation you have just learned from the previous slides. The process you have used was two streams including input and output and two components A and B and only one single reactions. Here is the other process including a system with 8 different components are there and 3 inputs and 4 outputs are there and several reactions. So how about the mass balance equations? Actually everything is the same, but you should use the summation term. This is the differential mass balance equation for the total amount. dmTD dt accumulation is equal to in minus out. All flow rates for input and all flow rates for output should be summed for the input and output. Of course, from the viewpoint of total amount, you don't need to think about generation minus consumption term. Let's go to the component version for differential mass balance equation. Almost the same. dm dt accumulation is equal to in minus out plus generation minus consumption term. Of course, you should use the summation symbol for all input stream and all output stream or all reactions. But the basics are the same. Accumulation is equal to in minus out plus generation minus consumption term. At steady state, those equations are simplified after considering that dm dt term is going to 0. So for the total amount, input is equal to output. How about the component version? Output is input plus generation term. The example, sugar dissolution. A bucket, here is a bucket, holds a large quantity of sugar. Water at 3 kg per minute is pumped into the bucket. The sugar dissolves in the water in the bucket, and the resultant sugar water at 84% sugar leaves the bucket at 3 kg per minute. The labeled flow diagram is shown here, and apply the differential mass balance equation for total amount and the component version of mass balance equation to this situation. Total mass of system here and dm dt accumulation is equal to in minus out is 3 kg per minute for the input minus 3 kg per minute for output. So dm dt is going to 0. It means there are no temporal change of the mass of sugar inside of the system. Then let's go to the component version of mass balance equations. There are no reaction there, so the mass generation of sugar and mass generation of water is going to 0. Then let me start with the component version of mass balance equation for sugar. dm sugar in system dt is equal to input flow rate minus output flow rate. So in this case, there are no sugar in the input flow rate because only water is introduced into that bucket. Minus, let me think about output. The total flow rate was 3 kg sugar, 3 kg per minute, and the composition of the output stream was 84% sugar. So 0.84 by 3 is the output term. Then the resultant value is minus 2.52 kilogram sugar per minute. It means every minute the 2.52 kilogram sugar disappeared inside of the system. Let me go to the other component mass balance equation. dm, C stands for water, W stands for water, dt is equal to input minus output. So 3 kilogram water per minute is introduced into the system, and total value of the output stream was 3 kilogram per minute, and 16% is occupied by water in the output stream. So 0.16 by 3 for output term. Then the resultant value is plus 2.52 kilogram water per minute. It means the temperature change of water inside of system is plus or increasing amount of 2.5 kilogram water every minute. The summation of those two flow rate should be 0, because we already recognize that the dm dt for the total mass of the system should be 0. Again, dm, the mass of sugar inside of system dt, plus dm for water in system dt is minus 2.52 plus 2.52 should be 0. This value is consistent with the value obtained from the total amount version of mass balance equation. Another example here, glucose consumption in a fermenter. A broth containing 28% glucose or sugar is fed to a fermenter at a constant rate of 100 grams per hour. Yeast in the fermenter consume glucose at a rate of 12.9 grams per hour. This is the reaction rate achieved by yeast. The fermenter becomes contaminated, unfortunately, with bacteria, which consume glucose at a rate of 1.4 grams per hour. This value is about the second reaction rate. What is the rate of change of glucose in the fermenter? dm glucose dt is the question. So let me think about the mass balance equation for glucose here. And dm dt is equal to in minus out plus generation minus consumption term. So dm glucose inside of system dt is equal to 20. Why 20? Because the total flow rate of the input was 100 grams per hour, and 20% is the glucose of total amount. So 0.2 by 100 grams per hour is going to 20, plus minus output, and there are no output there, and plus generation minus consumption. This is the summation of all reaction. Minus 12.9 grams per hour is consumed. I mean, plus 12.9 grams per hour is consumed in terms of glucose. So minus 12.9. And the other thing is 1.4 grams per hour glucose consumption. So minus 1.4. Then you could calculate the mass change of glucose inside of system in terms of rate. So the resultant answer or value is 5.7 grams per hour. Let's move from mass balance equation to mole balance equation in a general form. 2 stands for moles instead of mass. In this slide, mole balance equation is generalized from two components, A to B, two streams, input and output, and a single reaction A to B to multiple components, multiple streams, and multiple reactions. Even if I have said the generalization of the previous simplified mole balance equation, but nothing special there. Let's go to the mole balance equation, and of course these equations are based on the very basics of material balance equation. Accumulation is equal to in minus out plus generation minus consumption. So let me think about, let me show you how those material balance equation, or in this case mole balance equations, are working in the following examples. Okay, here is the example about the urea production. So urea, NH2, 2 carbon, oxygen. So urea is a widely used fertilizing agent made from ammonia. Commercially, urea is manufactured from ammonia and carbon dioxide. So here is the balanced chemical reaction equation. How many compounds are available in this reaction? Ammonia, carbon dioxide as reactant, and the urea and water as the product. That is the reaction number 1, even if we have a single reaction here. Two gas streams. We have two gas streams as input to reactors. One at 230 gram mole per minute, and the second stream is flowing at 100 gram mole per minute, and also the composition of each stream is given to you. 85, 15 for ammonia plus carbon dioxide, and in the second stream 80% CO2 with 20% water there. So where are there? Okay. And inside the reactor, ammonia is consumed at a rate of 180 gram mole per minute. So we have the value about the reaction rate for the ammonia consumption for the system performance specification. Then the question is that we should calculate the flow rate in the output for each component. Okay, here is the block flow diagram, and we have all specification about the input. However, we don't know anything for the output stream. So we should calculate the output specification variables. Okay, so let's do the process calculation. Can you remember what is the step A? Step A is to define the components for material balance equation, and then number of components is going to the number of material balance equation. So this is the step A. Then we have the balanced chemical reaction equation. So it is better to take the compounds as the components. The unit would be moles. So A for ammonia, and C for carbon dioxide, and U for urea as the desired product, and water is also reactant, and also actually not reactant, but it is available in the input. However, H2O is a kind of byproduct in the output. So we have 4 compounds. It means we will have 4 material balance equations. Let me check the degree of freedom before calculating the values. By using textbook, we could calculate it, and also by my method, Professor Song method, we could calculate it. Of course, the result should be the same. Let me start with the textbook method. This is the freedom, and this is the restrict. we have 4 variables, so 4 input variables and 4 output variables. So we have totally 8 stream variables. And then let's go to the system. In the textbook method, you should count the number of chemical reaction equation plus the number of accumulation term. This reactor is working on the steady state, so 0 accumulation. However, we have one chemical reaction equation. So here is the one freedom coming from the chemical reaction equation. Total number of freedom is 9. And then let's go to the restrict. Here are the specification for input 1, 2, 3, 4, 5, 6, and the specification for the inputs are 6. Is it right? No, definitely wrong. For example, 15% of CO2 could be calculated from 85% of ammonia, or 80% CO2 could be calculated from 20% water. So this one is not independent of this one, and 80% CO2 is not dependent of 20% H2O. So you should count this one, the total flow rate of stream 1, and one of the composition of the corresponding stream, and also the value of the total flow rate for stream 2, and one of the composition. So you should count those input. Specification is 1, 2, 3, 4. So for input. And how about output? Nothing there. There are no specification. We should calculate those unknowns. So 0 output plus, how about the system? I mean system performance specification. So here is the ammonia consumption rate, and that is the specification for the system. So 1 system plus 4 materials balance equations from 4 compound. So this is 9. 9 minus 9 is going to 0. Let's go to the Professor Song's method. Freedom minus restrict. So input, output, accumulation, the same thing. But in my method, I will count the number of consumption term and generation term. Let's go to the balanced chemical reaction equations. So you have 2 reactants and you have 2 products. So 2 consumption terms are available for the system, while 2 generation terms are available for the system. So 2 consumption plus 2 generation. The total number of freedom is 8, 10, 12. 12 freedoms are there, and let's go to the restrict. 4 input, 1 system variables, 0 output, and 4 materials balance equation, which are the same in the textbook method. And let me think about the relationship between consumption term and generation term. Let's go back to the balanced chemical reaction equation here, and you can find 4 different entities and 4 different stoichiometric coefficients. So we could get 3 different or 3 independent relationship between the consumption term and generation term. So I can write down 3 stoichiometric coefficient or 3 chemical reaction equation term. So the total number of restricts is 4, 5, and 8 and 12. So 12 minus 12 is going to 0. Of course, you should have the same value in terms of degree of freedom from the textbook method and also Professor Song's method. Okay, it's time to calculate the variables of processes. Okay, from this chapter 3, I'd like to use the extent of reaction xi instead of reaction rate A or B or something, or generation term, consumption term, or something like that. It is very convenient to use xi. So let me try to do it. What we know is the ammonia consumption rate. So I'd like to convert the reaction rate of ammonia consumption to the extent of reaction. So R dot, I mean molar flow rate, molar reaction rate of ammonia for the reaction 1 is equal to minus 180 gram mole per minute, which is given from the text. Why minus? Because ammonia is consumed instead of generated. Then, which is equal to the xi, the extent of reaction 1, with the stoichiometric coefficient of ammonia in reaction 1. What is the value for the coefficient? Minus 2. So minus 2 xi1. Then you can obtain the value of the extent of reaction xi for reaction 1. Okay, then let me use this value for material balance equation. The followings are the 4 different material balance equations for 4 different compounds. The first one is ammonia, and this process is based on the steady state. So you could kill the accumulation term or dNdt. So output is equal to in plus generation minus consumption. From now on, instead of generation minus consumption, I'd like to use the word just generation. Minus generation is consumption, so this is just generation. Then this is output is equal to out is equal to in plus generation, right? And then input term, let's go to the stream 1. Total amount is 230 gram mole per minute, and the 85% of this amount is devoted to NH3. So 0.85230 plus generation term. 90 from the xi, extent of reaction, and minus 2 comes from the stoichiometric coefficient of ammonia. Then you could calculate the output flow rate of the ammonia. Let's go to the carbon dioxide. So output is equal to input. For the cases of carbon dioxide, we have 2 input streams. So you should sum those 2 things. The first one is 230 by 15% and 100 by 80% here, plus generation term. 90 is the value of xi, or the extent of reaction 1, and minus 1 comes from the balanced chemical reaction equation. I mean the stoichiometric coefficient of CO2 in this reaction 1. Then you could calculate it. How about urea and water? You could do the same thing for the values of output. The total flow rate is the summation of those 4 things, and then finally you could get the value. Or you could use the mole balance equations for the total amount, and the value is 240 gram mole per minute for the total output stream. The second example for the mole balance equation here, and we are still working on urea, but from cheaper reactants. Urea can be manufactured from methane, water, nitrogen via a pathway requiring 4 chemical reactions. So the first equation here second equation, third equation, and fourth equation. So the problem text is saying that we have three different compounds as reactants. Again, methane, water, nitrogen. Let me check the raw material. Methane and water and nitrogen. You can find some intermediate generated during reactions. So let me try to obtain the overall chemical reaction equation from those four different chemical reaction equations. So methane plus water is going to carbon monoxide and hydrogen in reaction 1. Then in the second reaction, we have also carbon monoxide with water, which is going to carbon dioxide with hydrogen. So this carbon monoxide is generated from reaction 1 and also disappeared or consumed in reaction 2. And the other thing is we should go to the reaction 3. Nitrogen plus 3H2 is going to ammonia, and this ammonia is consumed at the reaction 4. So let me try to remove those ammonia from reaction 3 and reaction 4. So multiplying the both sides of reactions of reaction 4, so 2, 1, 1, and 1. Then you could remove those ammonia from reaction 3 and reaction 4. And this CO2 is also intermediate. And this 3H2 is removed there. And then also here is water, and then here is water. So the remaining thing is methane plus water with nitrogen as the reactant. And as the product, you could find hydrogen plus the desired product, urea. So this is the overall equation. So the raw material would be methane, water plus nitrogen. We'd like to design a process to make 90 gram mole per minute urea at steady state. So we'll have the 90 gram mole per minute urea as the upstream from the raw materials methane, water, nitrogen. Furthermore, there should be no reactant nor any intermediate leaving the process. So it means we have the complete conversion for the process. So in the upstream, you will have the urea here and hydrogen. The raw materials include methane, water, nitrogen as the raw materials. The question is, what should be the reactant feed rate and what are the byproducts? So 1, 2, 3, 4. Those 4 variables are our targets for calculation. So as the first step, let me think about the degree of freedom. As you know, we have 2 different methods for calculating the degree of freedom, by textbook method from chapter 2 and by Professor Song's method. As the step A, I'd like to define the components for materials balance equations for estimating the number of material balance equations. So I have said we don't have any intermediate and also reactant in the upstream. It means complete conversion. So in that case, we don't need to think about the intermediate. Therefore, I will focus on the overall chemical reaction equation. In the case of considering the overall chemical reaction equation instead of all of the 4 chemical reaction equations, we don't need to think about the intermediates like carbon monoxide, carbon dioxide, and ammonia. So we have the 5 different compounds like in this block flow diagram. 1, 2, 3, 4, 5. 5 compounds are there, and we could consider those 5 compounds as the components for the materials balance equation. What is the 5 components? M for methane, W for water, and N for nitrogen as the raw materials, and H for H2 byproduct, and urea is the desired product found in output stream. So we have 5 material balance equations. So let's count the degree of freedom by using the textbook method from chapter 2. Input 1, 2, 3. 3 input variables are there, and 1, 2. 2 output variables are there, and then let's go to the system. No accumulation because this process is working on the steady state. And then the other thing is the number of chemical reaction equation. I have said we will focus on the overall chemical reaction equation because we don't need to think about the intermediates. So 1 chemical reaction equations. So total number of freedom is 5, 6, 6. And let's go for counting the restrict and equations. I have said 5 material balance equations are there because we have 5 compounds expected from the overall chemical reaction equation. And one more thing, one more specification for the output stream. OR basis, 90 gram mole per minute urea. So one output specification. So 6 restrict, and 6 minus 6 is going to 0. Then we can solve this problem. Let's go to the second method by Song's method. And like in the textbook method, we have 3 input, 2 output, and 0 accumulation. Also, for the restrict, we have 5 material balance equation and 1 output. However, I should consider the consumption term and generation term as the system variables. So let's go back to the overall chemical reaction equation. We have 1, 2, 3, 3 reactants and 2 products. So 3 reactants indicate 3 consumption terms for the system variables, and 2 products indicate 2 generation terms for the system variables. So totally 5, 10. 10 unknowns or 10 freedoms are there. Let's go to the restrict. We should go to the chemical reaction equation again, and we have 1, 2, 3, 4, 5 entities. It means 5 stoichiometric coefficients for each entity. Then we could have 5 minus 1, that is to say 4 relationship between consumption term and generation term. So 4 restricts are there from the chemical reaction equations. So 10 minus 10 is going to 0. At this chapter 3, you have learned about the extent of reaction Chi. Then I'd like to introduce one more method for counting the degree of freedom. And also, this degree of freedom method is based on the process calculation for this example. In this case, I'd like to calculate the extent of reaction for reaction 1 and reaction 2 and reaction 3 and reaction 4. That is to say, I'd like to consider all of the 4 chemical reaction equations. So here I have written down 4 chemical reaction equations. It means we should consider all compounds involved in those 4 chemical reaction equations. It means we should think about the intermediates in addition to the raw materials and the product. So how many compounds are there for the all of the 4 chemical reaction equations? Methane, water, nitrogen as reactant, and hydrogen, urea as the product, plus 3 intermediates are considered as the compounds. So CO and CO2 and ammonia. So 8 components means 8 materials balances are available for these problems. So let me count the degree of freedom from chapter 3. Like in the previous 2 methods, we have 3 inputs, like 1, 2, 3. 3 input stream variables. And how about the output stream variables? Until now, we have counted 2 because we have urea and we have hydrogen. Also, when you are counting the restrict, this one is counted as 1 because it is the basis. However, in this case, let me say, we have already known that the flow rate of urea is fixed at 90 gram mole per minute. So I don't want to count the output, the urea flow rate as output variable. So just let me say the output variable is only 1. This is the hydrogen flow rate in the stream 2. So total number of freedom is 8, and we have 8 the mole balance equations, so it is going to drop. It is another or alternative ways to count the degree of freedom. Or you can say like that. The same thing, 3 output and 3 input and 2 output when you are considering those 2 things as the unknowns, and 4xi minus 8 materials balance equation with 1 output specification. That is the basis, this one. That's okay. Actually, every method is going to draw. Then let's do the process calculation. I'd like to following the textbook method from chapter 3. I mean, we'll use the 8 mole balance equations for finding 3 input variables, 1 output variables, plus 4 extent of reaction of reaction 1 and 2 and 3 and 4. So here is the mole balance equation. This is for M, I mean methane, and this is for the second compound, water, carbon monoxide, carbon dioxide, hydrogen, nitrogen, ammonia. Is it ammonia? Right, ammonia and urea. So 1, 2, 3, 4, 5, 6, 7, 8. 8 material or mole balance equations are available. And let me check what are the unknowns. So this one, the input flow rate of methane, and water, this one, and where's the nitrogen? Those are unknowns. And the other thing is one output variable that is for hydrogen. So here is the hydrogen. This is the unknown. And the other four unknowns are Xi1, Xi2, Xi3, Xi4. So from those 8 equations, you could calculate the 3 input variables about nitrogen, the methane, water, and nitrogen, and one output flow rate, hydrogen, and 4 Xi, 4 extent of reactions for reaction 1, reaction 2, reaction 3, and reaction 4. That is the process calculation for this example. This is the summary tables for the differential material balance equations. The first one is differential mass balance equations for total amount. The second one is differential mass balance equations for each component. The next one is differential mole balance equations for total amount, or total moles. And the last one is differential mole balance equations for each component. Okay, we have 4 equations are there, and you don't need to try to memorize them. The most important thing is accumulation is equal to input minus output plus generation minus consumption term.